Hello, everyone. The time is 2:56, and we'll be beginning in just a few minutes at around 3 o'clock. So, how is everyone doing today? I will also copy the link to the PowerPoint here in the comments since I was a tad late on getting those out to you guys. Literally just finished making all the blanks, copying it over to make your guys' version with all the blanks on it. So there's that for you in the chat, or maybe it's on this side. I don't know. I think it's on this side. Let me close the door behind me and we'll get started. But yeah, tell me how you guys are doing. How was your weekend? Let's see. In the meantime, I'm going to continue making up kind of a last minute little demo here that I thought to do. I was thinking about it last night and I was like, man, I really wish I had grabbed those, wooden fault blocks from school that are perfect for demoing this. Totally didn't, because when I was at campus like a few weeks ago, I was like, nah, I don't think I would use those. No, I've never used them before. And then like not long ago, I was like, why am I so stubborn about this? I should really just use those. But it's too late now because I couldn't get to campus by that time. It was the time that I decided to use them. It was too late. But that's okay because I can literally just make it right here, right now. Let's see. So Echo has been working hard cleaning up the barn. I almost worked hard and cleaned up this week and did not. I was thinking of weeding the yard. At least made the trip to Home Depot though and got the necessary things for yard work. So didn't really have them. Noah says he's good. How are the rest of y'all doing? I probably should have made like the drawings before I tore the paper. That's okay. Hindsight is 2020. Thanks, Captain Hindsight. You're such a hero. I don't actually like that show very much, but I thought that bit was hilarious. Noah's been working on a book. That's super awesome. You'll have to tell us what you're writing about. Is it like a fiction? Biography? Or nonfiction? So it is 3 o'clock. So we'll go ahead and as soon as I finish that, boom, got that done. So we will, science fiction, awesome. I'm not a big science fiction fan, but there's been a few here and there that are like really good. I'm also not a big reader though. Thanks, attention deficit disorder. It makes it extraordinarily challenging. But that's okay. For me, reading can be kind of painful practically. It's like take a normal person, however long it takes them to read something, times it by 2 at minimum. And that's the minimum time it'll take me to read the same thing. Minimum. But in any case, enough about that. Let's go ahead then and get started talking about earthquakes. I really love talking about earthquakes. One of my favorite things to do is to bring awareness to the topic, because there's also a lot of myths out there about earthquakes, and specifically about earthquake safety. We will be addressing that on Thursday when we meet at 3 p.m. for lecture. And if you guys don't remember anything about like anything from this class, remember the safety stuff and like the flood stuff, remember earthquake safety, what to do in an earthquake, what to do in a tsunami, what to do. Did we talk about what to do in a riptide? I hope so. But in any case, remember that kind of stuff from this class. But we have some other business to talk about first. Also, I'm going to be demoing kind of what you're going to be doing in the lab, since the instructions are, they're pretty good, but it's still confusing regardless. Even though the instructions are kind of decent, it's still very like you're reading it and you're like, I'm not getting it. So we'll demo that at the end of lab. All right, so I have the link to the PowerPoint in the chat comments as well as on Canvas. And let's go ahead then and get talking. Oh yeah, I need to make a Canvas announcement about this. I forgot to include it in my Canvas announcement this morning. But there is an extra credit opportunity this week. It is 10 points of lab points. And it doesn't matter which lab I add those 10 points to, because it all still goes in the lab points pool for when you're graded. But this is worth 10 lab points. That's half of a lab. So if you've missed a lab, or if you didn't do particularly well on a lab, or you are just, really want to make sure you get like the highest grade possible in the class, if you're competitive, or if you're like really looking for honors and stuff like that, or you're just gung-ho about this, whatever your reasoning, you can still do the extra credit. Anybody can do it. So the extra credit is to make an emergency kit. There are 2 links or 2 documents in the module. One of them is about making an earthquake kit, or a disaster kit, just something, an emergency kit. That's what they're really called. So it's about making an emergency kit, and what kind of things you would want to include in it. I recommend keeping one in your car, as well as keeping one in the house, knowing where the things are. And sometimes it can be good to have an extra spot in the home where all the things are located in one place. Then the other thing is not for extra credit. It looks very similar. It's from the same people made it. It's like an insert into that. It's recommended that you actually include this in your emergency kit, because during an emergency, it's very difficult to think, because you've got your adrenaline going and all that jazz. And so this is just gathering of essential information, all the things that you might forget during an emergency because you're freaked out. It's like contact numbers, so that you have people's numbers written down. I mean, how many people's phone numbers do you actually know? Like, what if you need to use a phone other than your cell phone? Stuff like that. And then also like addresses, like where's the nearest fire station? Where's the nearest hospital? And what's my doctor's phone number? What medications, might I need for the family or for myself? Things of that sort. I've actually filled out that same pamphlet, and I actually have it in my home as well. I actually just used a search engine online and looked up, where's the nearest police station? Where's the nearest hospital? So yeah, but there is 10 points extra credit for making a earthquake or a emergency kit. It doesn't have to have all the things that are suggested on the handout, but it, just those essential items, having some of those in one place, where they're at, and just take a picture of it and then send that to me, include it maybe in your lab or something. If you forget to do that, you can email it to me, whatever. It's extra credit. Have that done by next Monday. Yes, have it done by next Monday. So anyways, let's move on to the lecture slides. I really like talking about earthquakes because, again, it's another topic that's extraordinarily relevant here in Washington. Who was awake for or was woken up by the earthquake this summer? We had, I can't remember what the magnitude was, but we had kind of a small, very brief earthquake with its epicenter was in Snohomish. It woke me up. I always freak out in an earthquake because my first thought is just, how bad is it going to be? So Echo felt the earthquake. Anybody else feel that particular earthquake? Woken up, was really close to you, so the intensity might have been pretty intense there if the epicenter was close to you. First thought to hide under a desk, grab your brother and hide under a desk. Unfortunately, in my room, I don't actually have a table or a desk. My room is actually rather small, so there's not even really a spot for a table or a desk. But if you're in bed, I'll give you guys this tip. If you guys are in bed during an earthquake and there is not a table or a desk nearby, the best thing that you can do to protect yourself is stay in bed and maybe even just kind of, because beds are really soft and they absorb shock, and hopefully the one thing that you really don't want to do, if you have anything mounted over your bed, you've hung a picture there or you've hung some other decor that is, framed, something heavy, please move it and don't do it in the future. Because in an earthquake that can fall on you. And that's no good. It's also recommended that you not have your bed right next to a window, just in case the earthquake is a very bad earthquake and shatters the window. This earthquake, though, was so brief that the moment it started, it ended almost as quickly as it came. So there wasn't even really time for much reaction in that quake. At least it wasn't where I felt it all the way here in Linwood. But the shaking was pretty intense. The whole house shook, and it was a very brief, violent shake. Let's go ahead and talk about why we care about earthquakes. I think that because we live in a prone area, some of these reasons might be fairly at your fingertips because it's a very real thing for most of us here in the PNW. But why should we study earthquakes? Why should you care to sit here and learn about earthquakes with me? Some of the reasons that maybe come to mind. I just had some earthquake comments lag come in. The comments are coming through. I just had Echo and Noah's experience comments come through, but they're there. Make the dogs quiet. The way earthquakes happen away from plate boundaries, fissures and fault lines. We'll talk about earthquakes away from plate boundaries too. Hopefully today, that's kind of our stretch goal. if we can get there. So a magnitude 5. Magnitude 4. I don't remember what it was, but I know that 10 minutes after the earthquake happened and after I kind of calmed down, I was like, what am I doing? I need to get online right now and nerd out over the data because we actually have an incredibly great seismic network out here in the Pacific Northwest that covers pretty much the whole West Coast, actually. We have an excellent seismic network, and the data gets updated pretty much immediately. So I was like, I got to find out. Some of the data was incorrect and got corrected the next day as more data came in and whatnot. But so I was there sitting there at like 3 a.m. on my phone, like on Pacific Northwest seismic network. Like, how deep was it? You know? So I don't see any reasons in the chat about why we care about earthquakes, but it's 3:12 and let's move on. So some bullet points that I have about why we should care about earthquakes is, obviously, just like us, there are people who live in earthquake-prone areas. Also, we should study earthquakes and know about them because of the damage that they cause to buildings and roads. They cause damage in major earthquakes to like gas lines, which is really bad, and power lines, and just damage to all kinds of infrastructure. They also can cause other natural disasters to occur. So they can cause liquefaction, and in some cases, when they take place in the ocean or on the coast, they can cause tsunamis. We're actually going to talk about tsunamis on Thursday. I think I already said that, though. So then slides 3 through 5 show some devastation of some earthquakes. The slide 3 there is showing the devastation from the San Francisco earthquake that took place in 1989. I was 1 year old. And it actually killed 63 people and injured 3,757 people. That structure that you're looking at in there, in case you are wondering, there's this like freeway kind of stacked structure that you're looking at there. Yeah, the World Series earthquake. This was some people nickname it the World Series earthquake. Because it was actually very wonderful. So the Baseball World Series was taking place, and thank goodness, because this earthquake happened around like 5 p.m. during rush hour, 5 or 4 or something like that in the afternoon when it would normally be rush hour. And when the structure that you're looking at on slide 3, those photographs, it would normally be incredibly crowded, have been at that time incredibly crowded with traffic and all these people. And as you can see there, that structure is, it's 3 stories tall. So there's a road on the ground level, I think, or at least crossing roads on ground level. And then there's a stack above it going one direction, and then a stack above it going the other direction. But a lot of people had gone home early that day or had not gone into work so that they could watch the World Series. So traffic was significantly less, and there were a lot less deaths that happened and injuries that happened as a result. There was, it could have been a lot worse. And important to note is that structure is identical to the Seattle Viaduct. Everyone wondering probably, why did we waste so much money? We didn't waste it. Why did we use so much money building the tunnel with Bertha and, trying to tear down the viaduct? The reason why is because this structure that you're looking at here is virtually identical structurally to the viaduct. And in an earthquake, the viaduct would undoubtedly collapse and pancake on itself the same way as this structure that you're looking at here. And that's no good. Very much no good. So I don't know why both examples I have are from San Francisco, but they are. San Francisco is very interesting. It's in this low basin and is very sandy. The substrate is really loose, unconsolidated, sandy material. And as a result, waves are amplified there. So the shaking that you might feel anywhere else nearby would not be as intense as it is in those loose, unconsolidated, low-lying sandy basins that the waves are just so much, they feel and stronger and are so much more intense. The shaking is more intense. And that's why San Francisco has had some incredibly notable earthquakes. There was also the San Francisco earthquake of 1906, and that also caused a lot of fires, which whatever like wasn't decimated by the earthquake was decimated by the fires. So just a big tragedy there. Then slide 5, what you're looking at are examples of liquefaction. The top left photo of the car, that's nose is completely in the ground, is Christchurch, New Zealand, an earthquake that took place. Sorry, can't remember what year. Numbers are hard for me. Took place sometime within the last decade. As you can see, that car's not that old. But again, another area that was built on extraordinarily sandy substrate. And when the massive earthquake happened, the ground there liquefied and things literally sunk. I'm not sure where the bottom photo is from, but that shows an entire building where one side of the building and its foundation literally sunk into the ground during liquefaction from an earthquake. So let's go ahead and get into some more information heavy slides. Let's define some earthquake terminology. We very much need these earthquake terms. So let me get your guys' slide up here. Okay, so basically, what is a fault? We're going to need to know what a fault is for this. A fault is basically a crack in the ground, very large, that goes deep underground. Sometimes it doesn't exactly appear always as a crack as we draw it. Sometimes it's honestly like a really wide zone along which movement takes place. So sometimes there's just like this whole like kind of messed up, gnarled, thick area where stuff just got churned when basically, so one block of earth slides alongside the other. And another definition that you can write in there for fault that is nice and concise is the sudden movement of one block of rock slipping past another block of rock. So let me demonstrate this for you guys here with this guy here. So these are the fault blocks that I wish I had got. So here we have some continuous ground. There are some layers underground, right? Some layers of earth, different kind of rock. And then during an earthquake, what happens? Suddenly, one block of earth moves relative to another block of earth, and they slide past one another. And you can see that now I have offset the ground underneath. And this is useful for determining where an earthquake has occurred. If you see, messed up stuff like this, you're like, oh, hey, that's a fault because the substrate layers don't match up on either side. They are all shifted one to another. And there's several types of several types of faults. There's this kind of fault. Sometimes it goes this way. Sometimes it doesn't take place like this. Sometimes you just have ground, right, that moves side to side like this. We've got some slides dedicated to that. Don't worry. Some slides where you can take some notes on that. So let's see. Most faults are locked until there is a sudden slip. And what do I mean by locked? What I mean is that there usually is some kind of pressure building up during in between earthquakes. There's pressure that's building up for whatever reason, and the faults, or either side of the fault though, is like stuck on one another. So if there's a pre-existing fault, literally the things just might be stuck on one another until the pressure that's building up becomes so great that it finally gives way. So most faults though are locked in place until slip occurs, and then there's that slip motion. So seismic waves during earthquakes, seismic waves radiate out from, this is some blanks that you can fill in, radiate out from the focus. The focus is also sometimes called the hypocenter. Both terms are interchangeable. I don't know which term I tend to default to. I think I just use whichever term comes to my mind first. But I use both in focus, hypocenter. So that's the actual spot, because usually there is like a area underground where the slip initiates, and then it causes more slip to take place along the boundary, right? So we can actually tell too where the area is underground, where the slip initiated, even if it caused a lot more slip nearby and elsewhere and propagated along the fault. So that focus may be shallow, it may be deep, and that's one of the things that I got online to find out when the earthquake happened this summer. Is I wanted to know if it was really, really deep, like subduction zone deep, or if it was a shallow earthquake, and it was a shallow earthquake. It was not a deep one. So if you aren't prepared for a quake, it's all your fault. Oh my gosh, that's hilarious. I love it, Noah. It's great. I like puns. Puns and geology, just they're hand in hand, and it's honestly expected if you're in geology, especially if you're teaching geology, that you make puns. It's basically like expected of you. Or if you're a student, it's basically it's expected. Anyways, so seismic waves radiate out from the focus hypocenter where the slip initiates, where that slip begins. What is the epicenter though? Because you guys have probably also heard the term on the news, epicenter. Epicenter is different. Epicenter is the place on the surface of the earth right above wherever that slip initiated. Usually the slip does not actually initiate like on the surface of the earth. Typically it is deep. Deep. We use the terms deep and shallow, but what I just simply mean is that it typically doesn't occur on Earth's surface, like an initiate there. Typically initiates underground. However, the epicenter is basically like the epicenter was on, this street in Snohomish, or, located X, Y, and in X, Y, and Z like city. So if I wanted to tell you like the geographical location on Earth's surface where it occurred, and then the hypocenter is where inside Earth's surface, like deep down, it actually took place. Does that make sense to you guys? I hope so. So epicenter, spot on Earth's surface directly above the hypocenter or focus. Then there is just a really large block diagram there. The same block diagram, just kind of blown up on the next slide, showing the fault, also the fault trace, because normally the fault is 3D. It typically does traverse a long ways, to either side, right? So it's usually like the Seattle fault, for example, goes from like, one of the San Juan Islands, I believe, through Seattle and all the way to Bellevue. It's the same continuous fault, right? And there's, can be movement all along that fault or just parts of it. So there's some terms on there for you: the fault trace, the fault inside the Earth's surface, which traverses that whole length of the fault. There's the hypocenter, that spot underground, and then the epicenter, the spot above. And they've also labeled that those red things coming out from there are demonstrating the seismic waves. So let's move on to that next slide there and talk about causes of earthquakes, because different earthquakes are caused by different things, etc. So weak earthquakes, you'll see I usually abbreviate earthquake as EQ because it is difficult when taking notes to write out the whole word earthquakes. So I highly recommend using the abbreviation EQ. So weak earthquakes can be generated by things like volcanoes or landslides, or even meteorite impacts can generate like a really weak earthquake. However, destructive earthquakes usually occur because of tectonic motion. So now we're talking about on a much larger scale, that whole plate tectonic processes. So these destructive earthquakes occur because tectonic motion builds up stress in the crust. As these plates are slowly moving, right, especially if they are like at a convergent zone, they're going to be building up more and more stress as they slowly march towards one another. Or quake. Yeah, quake is also a good short abbreviation. Friction is one of these players. I have in bold below all of the players in these tectonic motion destructive earthquakes. So friction keeps the fault from slipping. Basically, there's friction between these two blocks of earth, right? And that helps keep them locked for a bit until stuff becomes too great. And then the slip initiates when stress overcomes that friction. And then elastic rebound, we've got another slide dedicated to this right after this. Elastic rebound causes the deformed rock to spring back into an undeformed position. So, for example, let's illustrate this. So talking about elastic rebound causing deformed rock to spring back to place from an undeformed position. Go ahead and look at the next slide there, and we're going to kind of show this. Think of like a rubber band that's continuing to be deformed, right? As you're putting energy into like stretching it out, and then you let go, and then it's like, hey, I don't have anything causing me to be deformed anymore. I'm going to snap back into my comfortable original position that I like to be at rest. Same thing if you were to take like a really rigid, like a stick or something, which is what they're illustrating there, with a person bending this stick. If the person bends it and bends it and bends it until the point when it actually fractures and breaks, either side of the stick is actually going to wiggle the moment that it breaks. And that wiggling there is the analogous to the shaking that occurs during an earthquake. And then after that energy is released, it goes back to rest in its comfortable, straight position. Let's see, did I want to illustrate this? I also kind of wanted to illustrate this at like, say, a subduction zone where we have like oceanic crust and then we might have oceanic crust on the other side, or we might have continental crust on the other side. As this guy subducts down below the other edge of the other tectonic plate, is actually going to drag the leading edge of the other plate down with it a little bit, so that over time it's going to be more like this dashed line that I just drew, right? And then enough stress and strain will build up that it's just like, I can't take it anymore, just like the stick. And it's like releases the pressure in a great earthquake and then goes back to where it's happy. We actually can demonstrate that this occurs using GPS monitors. And if you guys do the extra credit on the focus questions and learn more about slow earthquakes, you'll see how GPS monitors can actually track the motion of the plate as it's like kind of crunched back by the subducting plate. And then during an earthquake, it shoots back up, and as a result, the plates actually move, or the GPS monitors and the ground moves back to its original place, and you can see the monitors actually like move. Anyways, very fascinating stuff, geodetics. Love it. You got to be super smart though to go into geodetics. And by super smart, what I mean is you have to really love math, and specifically linear algebra. I don't know linear algebra. So I know calculus, new calculus. I'd have to relearn it and re-go over it, but linear algebra is just a horse of a different color. So anyways, let's talk a little bit about those different types of faults and some fault terminology. So we have what's called, because usually a fault does not propagate straight up and down. There are times when it probably can, but nature's not, doesn't like to be like 100% like a scientific model. Nature usually breaks on like at an angle, right? And because it breaks at an angle, we can then assign some terminology to this. Notice that this shape is wider at the top than it is at the bottom. Wider up here, smaller up here. This other guy is the exact opposite. It is wider at the bottom and not as wide at the top. That allows us to assign different names to these because they're shaped differently. So this wall right here, well, let's start with this one. This is the foot wall. The foot wall is the one who has the shorter top. You can say that it is it has like a guy standing too, like on the fault. So if you were to put like your leg on either side of this fault, your foot would be basically on this side, right? That doesn't really make any sense. But anyways, the foot wall is the one that has the shorter side, and the hanging wall is the one who has the wider top, where basically if it were to go like this, it'd be like hanging, right? If I were to do this, this one isn't hanging. Do you see that? How this guy, because it's got a wider top, it's overhung, kind of like oversteepened or undercut. So that is the hanging wall. Hanging wall is easier to remember than the foot wall. So let's talk about what a normal fault is. And we call it a normal fault because this is the more common type of fault. So a normal fault, at least I believe that's why we call it. Maybe I'm wrong on that. But anyways, a normal fault is where the foot wall goes up and the hanging wall goes down. So hanging wall moves down relative to the foot wall. And this develops also what we call a fault scarp. So this surface right here would be called the fault scarp. And you can see it labeled on your diagram as well. And let's see. Yeah, I think that's all the terms I would like to go over. So, oh no, this typically takes place in an area where the crust is being kind of like pulled apart. So as I pull this apart, usually in order to accommodate that stretching motion, we get normal faults that occur where the footwall goes up. So that takes place when there is stuff pulling it apart. So let's go ahead and look at what a reverse fault is on the next slide. A reverse fault takes place in a compressional tectonic setting where the crust is being crunched together, and usually the footwall is going to go up. So the hanging wall. Hanging wall moves up relative to the footwall. And yeah, takes place in that compressional environment. And in this case, the fault scarp is going to be overhung, right? It's going to be like this little overhang. And let's talk about a thrust fault. A thrust fault is also a reverse fault, but it is specifically a low angle reverse fault. So typically, instead of something like this, where see the angle of this fault is more like, I don't know how many degrees that is, but it's not too far from vertical. It's, just a little bit off, right? It's just a little bit off from vertical. A low angle reverse fault called a thrust fault is when it's like this and it's almost horizontal. Not almost, usually about 30 degrees is typical for a thrust fault. So 30 degrees on this surface. Right now it's about probably 60 degrees what I did here. I'm not a very good estimator. Don't quote me on that. So this also takes place in a compressional environment as well. Are they usually rare? Yes, Alicia. Thrust faults are not as common as the other two types of faults. And we do typically see them more with greater tectonic forces. So like at a subduction zone, there have been a lot of low angle thrust faults here in the Pacific Northwest. And some of these low angle thrust faults back in history were responsible for bringing ocean crust actually up onto the state of Washington and accreting it onto the edge of our state. So if you go up to Washington State Park by Anacortes, you can actually go up there and put your hands on stone that was initially in the ocean and got shoved up here from a low angle reverse fault, a thrust fault. These are usually powerful, create more powerful earthquakes. And yeah, I don't want to be near a thrust fault when it goes off. But unfortunately, we live here in the Pacific Northwest. Let's talk about the last kind of fault, which is a strike slip fault. So this is where these strike slip faults do tend to be vertical. The fault does tend to be vertical. And the motion is taking place side to side, like this, as opposed to up, down, it's going side to side. And thus there is usually not a hanging wall, there is not a footwall, but the blocks move alongside one another. And this is responsible for causing fences to be offset from one another, or telephone poles or train tracks. If you take a look, we'll see some fence posts that's been offset in like a few slides. And then there's also, we won't really go over it, but if y'all want to know, there's a left lateral fault and a right lateral fault. Basically, the block opposite to you, did it move to your left or did it move to your right? And that will define left lateral or right lateral fault. So let's go ahead and talk about causes of earthquakes at convergent plate boundaries. We will get to earthquakes not at convergent plate boundaries in a minute. But let's first talk about at convergent plate boundaries. So convergent plate boundaries generate compressional forces because, again, you have two tectonic plates that are converging. So large earthquakes are associated with mountain building and faulting. So basically, what I'm trying to say in this bullet point is that convergent plate boundaries have really large earthquakes. And these really large earthquakes are associated with building the mountains that we have here. The subducting plate forms a megathrust fault. We live on a megathrust fault, guys. It's kind of terrifying. That's why we're all worried about the big one, is because it's from the megathrust fault. It's basically that plate that's subducting underneath the edge of our continent is a low angle reverse fault. It's a thrust fault. And it's very gigantic because it traverses the entire coastline. So we call it a megathrust. Megathrust earthquakes are the ones that produce the most powerful earthquakes. So a megathrust earthquake was responsible, or a megathrust fault rupture was responsible for generating the Tohoku earthquake back in 2011. That magnitude 9 point something, which by the way, we actually, the geologic community didn't believe that magnitude 9 point whatever earthquakes, 9 and above, was actually possible until the Tohoku earthquake proved them wrong. And they're like, oh, I guess it's not just conceptual. I guess it can really happen. So let's go ahead and look at the next slide there. I have some photographs of some transform plate boundaries. And what you're looking at there is the San Francisco, or not the San Andreas fault. Sorry, I was thinking about San Francisco because I just had to text my brother today. I was like, when I was going over the San Francisco slides, I was like, I don't know if my brother knows about how San Francisco is different than Washington, that particular city in that sandy basin. And so I texted him and I was like, here's what you should do during an earthquake. And you should know that earthquakes there in the city are not the same. So in that slide there, you can actually see how there has been offset on either side of the fault, moving side to side as opposed to up or down. You can see that the fence has been displaced. There is a fault running right in between that fence and ruptured one day. And the farmer was like, well, I guess my property line changed and I need to reconnect my fences back together. And also you can see in the aerial photograph there of the San Andreas Fault that in certain parts, the mountainous area doesn't, on the right-hand side, doesn't match the left-hand side. Like one side is really mountainous, and then completely opposite that large crack, it's not. And that's because it's literally moved mountains apart from one another and areas of high topography apart from one another. So in the Pacific Northwest prepared for a massive, is the Pacific Northwest prepared for a massive earthquake? Yes and no. In certain areas we are, like in new buildings, we are prepared for larger earthquakes. I can't say about like a magnitude 9. I do worry about skyscrapers in the Pacific Northwest and a magnitude 9 earthquake. because we don't implement all the same techniques as the Japanese do. So in Japan, during that magnitude 9 earthquake, not a single building fell. Not one building fell in that magnitude 9 earthquake. And it is because they're so earthquake prone. And their government, has just thrown money at earthquake research and earthquake engineering, because it's so vital to their survival there, because they're so frequent and they're large too. So they've invested a lot more money than we have into earthquake preparedness, infrastructurally. However, what they were not prepared for, unfortunately, was a tsunami. And the tsunami is actually what caused the greatest loss of life in that event, as well as it is also what caused the meltdown at the Fukushima power plant, because the water got into the nuclear power plant. And that is what caused the nuclear meltdown to occur. It was not the earthquake, it was the tsunami. So we're definitely prepared. Modern buildings do have pretty good codes, though, for earthquakes. So if you're in like a modern building, you should feel, if it was built in your lifetime, you should feel pretty safe. And even if it was built kind of a little bit before your lifetime, because I forget, some of you guys are young, really young. Some of you might be running start students, but like if it was built within the last, I want to say like 40 years, and even the newer that they are very earthquake safe. The Lake Tai building is incredibly earthquake safe. The Lake Tai building is where we would normally meet for this class, had the virus not come out and thrown a wrench into everything. So yeah, we are and aren't prepared. In some respects we are, and in others we aren't. Getting rid of the viaduct was a big help in earthquake preparedness. So let's go ahead though and look. I can rant on about that. So let's move on though, to talk about causes of earthquakes at transform plate boundaries. So transform plate boundaries, remember we talked about back in plate tectonics that sometimes the edges of two tectonic plates are not moving towards each other, nor are they moving away from each other. Sometimes they're moving alongside each other, and that causes these strike-slip faults along those transform plate boundaries. Yes, the San Andreas fault, I believe, is actually like, I believe it is a plate boundary, or it's at least, no, I don't think it's it's kind of, I don't know how to classify it, because honestly, the San Andreas fault motion is, I don't know if I want to classify it as, I don't know what it's really classified as, but it's basically gigantic. It's a really big deal, the San Andreas fault. In any case, transform faults, aka these gigantic strike slip faults, they can have like a lot of branches off of it, and they can also have a lot of like fractures in it along the fault. And basically you'll have segments. So transform faults have many branches and fractures, and they also have segments in them. So as a result, offset occurs in distinct segments along the fault. Typically, the entire San Andreas fault does not rupture in one event. Usually it is part of the San Andreas fault that will rupture in an event. Same with just these transform plate boundaries. Only segments of it will rupture. So some segments displace slowly with little shaking during fault creep. So Some of these segments will displace not as fast and don't have a lot of shaking. And we can call that fault creep, where the fault isn't really moving a ton. It's moving just a little bit. Some segments produce numerous small earthquakes. So you could get like a little earthquake swarm. And some segments are locked for hundreds of years. And remember, locked meaning that there's just stress building up there, more and more and more pressure and stress. And it'll be like that for like hundreds of years because the friction is keeping it locked until finally, like 100 years later, so much pressure has built up that it does rupture in a large earthquake. So earthquakes also can occur in, or earthquakes along transform faults occur in repetitive cycles. So you can typically be like, it's time, we haven't had one and we're getting close to about how often these earthquakes occur. They really are pretty cyclical. Rupture usually propagates in a really quick time period. So it doesn't move for like a really long earthquake. It's usually like really quick, very short, very brief movement. As in, regardless of how much movement there is, it typically takes place like that. That's what I'm trying to say there. So rupture propagates very quickly in a short time period. You know how some earthquakes can go for like a few seconds and some earthquakes go for like minutes. Those are terrifying. I remember is anyone here old enough to remember what was it called? The earthquake that happened back in like 2000 or 2001. What was that called? I don't know why the name is escaping me. I usually remember it. Nisqually, the Nisqually earthquake that took place in the year 2000 or 2001. Anybody remember that? Y'all probably too young. Y'all probably running START students and are like, Caitlin, I wasn't alive. But anyways, let's go ahead and take a look at the next slide now that we've finished kind of filling in the blanks there. Yeah, it was terrifying. I was in like 6th grade at the time, and the earthquake, oh gosh, I remember the shaking wasn't that long, but it felt like 5 minutes. It didn't actually take place. I can't remember how long the shaking was. It was a little bit longer. It wasn't like that, like the one in the summer. It was super like just a few seconds. It literally, I think it went on for like a minute or maybe like half a minute. It went on for more than just a few seconds, and it felt like 5. So I can't imagine being in an earthquake that went on for like 2 minutes or longer. It must just feel like an eternity and be terrifying the whole time. But anyways, let's go on to slide 18 and talk about earthquake waves. The biggest earthquake can last for hours. Actually, the biggest earthquakes, are they the biggest? I don't know if they're the biggest, but some earthquakes can actually last for months. Yeah. If you guys want to know about those earthquakes that happen for months at a time, believe it or not, they happen here. You've experienced them about every 14 months for your entire life. They don't really shake. They don't really produce shaking, and that's why you don't know about them. But in any case, we do actually have earthquakes here that go on for like from hours or like 2 months, and they're called slow earthquakes. Again, that's what those extra credit questions are about. We won't be covering them in this class because you don't usually cover them in 101 classes, but they're super cool and you guys should totally learn about them. But on to slide 18. The study of earthquake waves is known as seismology. So seismology is the study of earthquake waves. I took a seismology class. It's all linear algebra. I almost failed it. Sorry, Walter. I really should have taken linear algebra before I took that class, but I didn't know that you needed linear algebra. And I should have just withdrawn on the first day, but I was stubborn. In any case, I should have switched classes, but I didn't. So anyways, I learned that, the study of seismology is incredibly difficult. So waves are measured by these nice equipment that we call seismometers. And in case you wonder how to spell seismometers, I will type it here in the chat for you for filling in that blank there. I can't spell seismometers. Maybe I can, I don't know. No, I can't. Google doesn't even recognize it. That's funny. It's trying to be like, do you mean thermometers? No. I mean seismometers. So inertia, let's chat about inertia. Inertia, physics term there, keeps a weighted arm from moving while ground motion moves the instrument. So basically the needle, you'll see kind of like in this picture, if you want to look at the next slide there, can you see the needle in the next slide? Barely, because it's so thin. There's a needle that's on top of this large drum, right? That is recording, it's circling around, right? Over and over. And the needle moves down over time, right? Basically, the needle actually stays put during an earthquake, and the rest of the equipment, the rest of the seismometer machine moves, right? And that's how the earthquake gets recorded. So it looks, in an earthquake, it looks like it's the needle that it's moving, but it's you. You're the one who's moving. Inertia keeps a weighted arm from moving while the ground motion moves the instrument. And the seismometer amplifies ground motion. It makes it look bigger than it actually is, so that you can see it on the seismograph, which is the there's basically paper wound around the drum that you're seeing there. And when you pull that piece of paper off and you're like, hey, look at these earthquake waves that are all squiggly lines along here, that piece of paper is called the seismograph. So go ahead and look at slide 19, and then you can see just another seismograph there. Is it the arm? I don't think the arm moves. Maybe it's the drum that moves. Sorry, guys. In any case, like what I mean by that is maybe it's the drum that moves along while the needle just stays put the whole time. In any case, let's talk about seismic waves. So, we're doing really good on time, guys. Yeah, we're doing good on times, and it's almost time for the slinky demonstration. I hope I can do it by myself. I don't know. Normally I ask a student to like hold the other end of the slinky, but I don't have a student to hold the end of the slinky right now. Anyways, let's talk about seismic waves. So there are two main types of seismic waves that are generated by earthquakes. They have their subcategories because each one has sub waves that are generated that are different, but there are two categories of waves. And the two categories of waves are body waves and surface waves. What are body waves? Body waves are the waves that travel through the earth itself. So you can see in the diagram that's included on that slide, the earth with a little wedge cut out of it, and you can see these lines that are going through the earth into Earth's interior. Those are body waves. They travel through Earth's body. There are surface waves. Surface waves travel in the rock layers just below Earth's surface. So they travel along the top of the crust, but they do not go into Earth's interior. And those are illustrated by that bright teal cyan arrow that is going across the Earth's surface. They don't penetrate down into the Earth's interior at all. And then there are two types of each that we are going to be talking about. So let's go ahead and move on to the next slide there, slide 21, and chat about the two types of body waves. So there are two types of waves that traverse through Earth's interior. The first kind of wave is called primary waves, abbreviated P waves. So primary or P waves. So these waves are a push or a pull. They pull rocks in the direction that the wave is traveling. So maybe I can like affix this. I should have found a way to like affix. I have a slinky here, and I should have found a way to maybe like affix this slinky, but that's okay. We're gonna try it right here. All right. So it travels in the direction that the wave is going. So if this length of this slinky is the direction that the wave is propagating, the push-pull occurs in that direction. It doesn't occur like side to side or nothing. It's just in the direction that the wave is traveling. That top block of Earth there that's broken up into a nice grid illustrates the motion, and we're going to demonstrate it too with this slinky in just a moment. There is a temporary change in volume of the Earth material that it is traveling through. Volume meaning like, is it like a large volume or a small volume? Because this is a compressional wave. So temporary change in volume of material because this is a compressional wave. These waves can travel through solids, liquids, and gases. And that's very important because that is in contrast with secondary waves. So let's see if I can demonstrate a compression wave for you guys. I don't know. I don't know about this. So basically, I don't know if you guys could see it very well. Maybe there is a better demo on YouTube that I can find and post for you guys. So what I want you guys to be seeing is that when I let go of part of this slinky, there will basically be like a compressional area that traverses the whole length of the thing, right? Let's see. I don't know. You guys may have to like slow down this video. It works a lot better when you do it in class and it's really far away. You can really see it very well. Let's see. I don't know. You guys might be able to kind of see it. I'll try to post a video online. Maybe I'll make a short clip of me actually doing it at home on a larger scale. And then let's talk about secondary waves, or S waves. You will see primary waves abbreviated as P waves from basically here on out, and you will see secondary waves abbreviated as S waves from here on out because it's so much easier. But They are called primary and secondary for a reason. Primary meaning first and secondary meaning second. So secondary waves, or S waves, shake particles at right angles to the direction that the wave is traveling, right? So basically, this could be illustrated with the motion of a slinky by doing this. Let's see if I can get this to show up here. So the wave is traveling this way, right? And I am moving the ground at right angles, 90 degrees up, down, right? This isn't really a compressional wave. Unlike, me trying helplessly to illustrate the compressional wave. So this does change the shape of the material, but it does not change really the volume of the material that it's traveling through. And it does not travel through liquids or gases. It only travels through solids. Why is this important? Because this is what allowed us to discover that the Earth had an inner core and an outer core, and that the outer core is liquid and that the inner core is solid. So because secondary waves do travel through Earth's interior, however, they don't travel through part of Earth's interior. Why? Because it's not because it's not solid, and it'll only travel through solid materials. So the fact that part of Earth's interior is liquid, the outer core, then when they began studying seismic waves and seismic wave reflections, which is basically what you're looking at, all those arrows on slide 20 in the middle of the Earth. If you go back to slide 20, you can go ahead and look at how the waves, all the lines that they drew, are bending just like all over the place. That's seismic reflections. And you can study seismic reflections with seismograms. And that allowed them to determine that some of these waves were not, the S waves were not traveling through part of Earth's core. And they're like, oh, hey, there's two separate layers down here. And it was actually a female scientist who discovered that, Inga Lehmann. And she must have been quite the character, because she must have been really terse. It says that she had a low tolerance for people who didn't understand the math and the stuff, and who were supposedly like up there in the upper echelons of scientists. If they didn't like understand stuff, she had a really low tolerance for them. So she must have been an interesting person. Anywho, let's go ahead and look at slide 22. And right here, we are seeing the illustration of that slinky, how I was showing the, trying to demonstrate how part of the slinky, as it travels through, will be like compressed as it moves down the length of the slinky. And then you can illustrate an S wave by shaking a rope, or even, quite frankly, a slinky as well, up and down. And that's just showing how the particle motion is different. In P wave, the particle motion is along with the length, right? It goes this way, the length of the wave traveling motion. However, with an S wave, the particles, which would be like the individual slinky things, go up and down, right? Instead of compressing this way, as with a P wave, we're talking about up and down. All right. So, Alicia kind of saw the compressional thing. I'll try to take a video later because it's really cool to see it. But anyways, if you have a slinky at home, go ahead and play with it. and try to see the different waves. So let's talk about the surface waves now. Let's take a look at slide 23 there. So surface waves, there are two main ones. There are Rayleigh waves. So that's the first orange bullet point there that begins with R. How do you spell Rayleigh? That's right. That's another weird word that you guys probably have no idea how to spell. Ray. Oops. Oh, wow. Somehow Google recognizes Rayleigh, but it doesn't recognize seismometer. Anyways, so I've typed in there how to spell Rayleigh waves because it's kind of weird. Rayleigh waves travel along Earth's surface like rolling ocean waves. So these are really bizarre. We have some more blocks there. You can kind of move that picture that's sort of in the way because when I normally teach this class, I have it on animation and you don't see the picture that's on top of the other graphs first. So you can move that if you want. Rayleigh waves, if you look at the graph or the block of Earth that's kind of hidden underneath it, this looks very much like an S wave. However, what I want you guys to notice that is different is that rather than just up, down, this it's kind of like a combination of the P wave and the S wave where the particles travel in like a circular motion. Do you see how I'm kind of doing that here where there is both up and down as well as motion in the direction of the wave that it is traveling, right? And it does this weird circular motion and it is bizarre to see the Rayleigh waves. The Nisqually earthquake, I went to a school that is perched above part of 405 and some of the kids after the shaking kind of stopped, like the shaking that we could feel in the classroom anyways. After that shaking stopped, some of the students went to the back window of the classroom and looked outside and I was still clinging to my chair for dear life because I was terrified. But some of the students actually went to the back window and were like, whoa, look at the freeway. And they were looking at 405 down below. And what they were looking at were these Rayleigh waves. And they were seeing the freeway kind of like churn like an ocean wave. And now that I'm a geologist, I'm so upset with myself for being too scared to like look out the window and see the Rayleigh waves. Probably a once in a lifetime experience and I missed it, but whatever. So these shake particles at right angles and direction to each other. Where did I leave off? Oh, I'm on the wrong slide. That's why I'm like, where am I looking? Okay. So let's talk about love waves now. Also in that other picture that was on top of the other picture, hopefully you've moved it by now, you can see they drew these red circles, right? Showing that the particles of Earth actually travel in this like circular shape rather than just up, down, side, side. And you can see these giant cracks like forming on Earth's surface as a result of the rolling motion. Anywho, let's move on to love waves. So the next type of waves are called love waves, and they are spelled L-O-V-E, love waves. These are very interesting. These ones, they don't go up, down. They don't go this way, nor are they a rolling motion. These literally are side to side motion. So, and that's illustrated in that block diagram there where they've broken up the Earth particles into little cubes, and you can see them moving side to side from one another. So move Earth's materials from side to side. These are the most damaging types of earthquakes. So, or of waves, not earthquakes. They take place in, I think, all earthquakes. But these are the most damaging types of waves, most damaging type of ground motion. That side to side movement really messes with earth, with foundations. It messes with roads and infrastructure, right? Those rolling motion waves, they don't do as much damage because typically things on the ground just kind of wobble to accommodate. However, the side to side motion is a whole different matter. Those will crack. They just cause a lot more damage. So let's go ahead and move on then and look at slide 24, which is a brief summary of these types of waves. The two on the top there are those body waves, the P and S waves, seeing those two block diagrams, and then looking at the bottom two block diagrams, you're seeing the Love and Rayleigh waves. I know they're kind of switched in that diagram. I really should switch this back. Sorry, guys. But the Love waves are up on top and the Rayleigh waves are on the bottom. And you can kind of see those again illustrated in that Earth diagram. Nice summary there. Let's look at slide 25. So seismic waves, their speed is very different. So some of these run really fast and some of these run really slow. And each wave, each of the body waves and each of the surface waves, all of them travel at different rates. So they all run at different speeds. The P wave is always the first, it is the fastest traveling wave, which means that it's going to be the first to arrive somewhere. And it's going to be the first wave recorded by a seismogram. And S waves are the second fastest type of waves. So the next wave that's going to be recorded on a seismogram is an S wave. Surface waves are the slowpokes. And it's very difficult on a seismograph to tell the two apart. Honestly, I don't know how you tell the two apart on a seismograph, but as you can see in the picture below, those surface waves are far more they cause a lot more needle motion. So you can actually see these different waves. So you see the P wave first there. It's this short little, the needle doesn't move very much. And it's usually like a very quick burst, right? Seeing that P wave there. And then there's some time. It depends how far away you are from the earthquake. Because, if you have 4 runners on a track, right? And one of them is really fast, one of them is slow, and then there's 2 really slow runners. The farther, the more they continue to run, the more exaggerated that distance between the two is. So the P wave is going to, if they've been allowed to run for a mile, the distance between the P wave and the S wave is going to be quite large. Whereas if you're right next to the starting line, they haven't really gotten too far apart from each other yet. So speed travel is very different for each type of wave. So looking at slide 26, P waves are faster than S waves, as I just said. You can fill in those. I believe they are blanks on your slides. Let me take a look at your slides. I forget which things I leave blank. Yeah, P waves are faster than S waves. And there you're seeing some different seismographs, right? You're seeing one from New York, one from Alaska, and one from Mexico for the same earthquake. The difference in arrival time is exaggerated by distance, just like what I was talking about. If you pass someone on the freeway, you're going 65 and they're going 60. The longer that you're on the freeway for, the farther ahead of them you're going to get, because you're traveling at 65 miles an hour and they're traveling at only 60. So if you're going like from Linwood to Everett, for example, by the time I get to Everett, I'm going to be way farther ahead than if, like, by the time I get to North Everett, I'm going to be way farther ahead of someone if I'm the one who's going 65 than if someone is going 60, right? If I'm at South Everett and I haven't quite gotten to North Everett yet, the distance won't be as far because I haven't been driving as long. So this helps us in finding how far away a seismograph station, how far away that station is from the earthquake itself. And this is very important because your lab relies on this knowledge. That's why I'm stressing it so much, is because your lab depends on that being a fact. So difference in arrival time is exaggerated by distance. A greater interval between the P and S wave, so a greater time interval between the P and S wave arrival, is going to indicate a greater distance from the epicenter, where it all started. So let's look at slide 27, and here is where I am going to demonstrate for you guys how to do your lab. Notice that I demoed it and kind of not at the end of lecture, so that people who might not be watching lectures have to like hopefully watch the lecture to find the demo. I don't know if anyone's not watching these though. I hope you guys all are. So what you're looking at there is a wedge diagram on the left-hand side, and on the right-hand side, you're looking at the seismographs. We need to talk about what a wedge diagram is. Let's go ahead and look at some seismographs though. I have some here. I've written notes all over them, but that's okay. So basically on these different seismograms, let's just take a look at the first one here. Hold on. Because the first one here is so nice. In these seismographs on your lab, you are not going to be, they cut it off just after the S wave arrives, and they aren't really showing you the surface waves, the Rayleigh or the Love waves. They're really only showing you the P and S waves here because that's all you need to find out how far away you are from the epicenter. So here we have the P wave arrival. We can see that everything is nice and calm. There's a little bit of noise on our seismogram that was recording this, and then the P wave hits. I don't know what this guy is. It's probably a little artifact. But anyways, then there's some shaking, some residual shaking after the P wave gets there. And then the S wave hits. And notice that the S wave is always slightly bigger than the P wave. You'll see that on your other, in the lab, on your other charts as well. So this is a really old lab. That's why it says changes needed at the top of it. So basically, this is quite a distance. That means we're probably pretty far away from the epicenter, right? And what you're going to end up doing is you're going to figure out what time this was at. I have it labeled at about 19 minutes right there, because this is, starts at like 15 minutes and this says like 19 here. You just need to know like how much time took place, like how many minutes this was for. You don't need to know what time it was, you know, it doesn't matter if it was 19 or if it was 20 or 80, whatever. You just need to know what that gap was between here and here. And in this case, it's about 1, 2, 3, 4, almost 5 minutes. Right? So yeah. So it was almost Yeah, it was almost about 5 minutes difference. Not quite though. And you're going to want to be accurate in trying to decide how many minutes passed in between here. You're going to want to be accurate about, don't round to 25. Your graph, your end result won't be as good. I've been meaning to insert more tick marks here, but I haven't had the time. So I keep forgetting, honestly, is really what that comes down to. And I remember at the last minute when there isn't time to add it in. But do your best. So basically, you're going to calculate how much time there is in between the arrivals of those waves. You're going to record it on a chart that's on page 2. There's this nice chart where you can say the difference in between the time intervals. So 4 minutes. I know I told you guys not to round, but for the example, I'm not going to take the time to determine and give you guys my numbers for what I guessed it to be, what I estimated the arrival time to be. But for now, let's just estimate it at 5 minutes because that's going to make demonstrating this a little bit easier. So now that I know that the arrival time between the P and S wave was 5 minutes, I'm going to go over to my wedge diagram. This is the same diagram that what you're seeing there on the slide 27 on the left-hand side, where you got these two lines, right? One of them is labeled S and the other one is labeled P. And on this side, we have travel time in minutes. And then on this side, down below on this axis, we have epicenter distance, right? So I'm going to use this one right here. Well, I don't really want to use that one because it's got their scrap piece of paper on it. But anyways, what you're going to do now is grab a scrap piece of paper. Boom. Got my scrap piece of paper here. And you're going to set it, you're going to line it up at the corner of this diagram here, straight edge. And notice how the axis starts at 0 and I've got like 1, 2, 3, 4, 5. I'm going to make a mark on my scratch piece of paper right at 5. So from the edge of the paper all the way up to 5. Sorry that I can't like hold it up and do it. Maybe I can hold it up and do it at the same time. I'm gonna clip this on here. Da-da-da. So I'm gonna line this up so that basically 0 and 5. Boom. 5 minutes there. I have marked a little dot on my piece of paper to show that this distance from the edge of the paper to where I put my dot represents 5 minutes. Now, here's the fun part. You are going to take this piece of paper here and you are going to slide it along these two lines. And you're going to want to make sure that your piece of paper isn't askew like this. You want to make sure it's actually straight up and down. I'm not really taking the time to be super careful here, but you are going to slide it until this edge, this corner of the paper rests on the P line and the dot that you made representing 5 minutes rests on the S line. And then you are going to mark a straight line down to the bottom axis. Once you find that spot where those two rest next to each other, and this is why it's important to be really accurate on this diagram, because if you're not, your arrival times are going to be really off, or your distance is going to be really off. So you want to be very accurate here. So once I find that spot where that rests, I'm going to draw a line straight down onto this axis here. And then that bottom axis there is going to tell you distance from the epicenter for that location. So let's take a look at the last page of your lab, because that is the answer for the first seismogram. But I want to see you guys. You'll have to print this lab out, unless you are very familiar with some editing software and have an incredibly strong preference for drawing your lines and your circles with a computer. I suppose that would be fine if you want to do that. But I am a by hand kind of person, so I would totally like print this out myself. So basically, Balboa Heights is the example. They use the first seismogram as the example, and they give you the answer right here. So they took their scrap piece of paper right here, and they found, they basically took 4 minutes and 50 seconds, because they estimated it at 10. I estimated it at 5, which would be really off. Please don't estimate it at 5. They estimated it at 4 minutes and 50 seconds. And they marked their piece of paper with the distance of 4 minutes and 50 seconds. I don't know why they have their paper like off like this. Don't do it that way. That's just sloppy. Do it the way I showed you. So then they took their piece of paper and they have slid it to where it intersects the P and the S lines. And then they have drawn straight down and found the spot right here, just past 3. And that tells you the distance to the epicenter in this unit, right? So units are really important. So that's times 10 to the 3rd kilometers, AKA far away, very far away. And you'll get to see how far away as you're doing the lab, because you're going to find where the epicenter of this earthquake was using these 3 seismograms and a wedge diagram. And then you're going to draw some circles on a map. Once you have figured out the distance to the epicenter, right, you're going to end up drawing 3 circles on your graph. You can also, where's the book? Oh, darn it. I left the book in the other room where I was working earlier. You're going to have on the United States map there, well, it's really just the North America. But anywho, on your map, which I have just drawn a very crappy one of, imagine that's the North America. You're going to find Boulder, Colorado. You're going to find Mexico City. And you're going to find, it's not on the northern hemisphere that I drew, but you're going to find Panama, Balboa Heights in Panama. And basically, you're going to draw a circle around each one, because you don't know which direction the earthquake came from, right? You only know how far away it was. So for there's example right here of Balboa Heights, they got 3.2 times 10 to the 3rd kilometers away, right, from the epicenter. But that didn't tell them which direction it came from. You cannot tell from a seismograph which direction it came from. That's why you need 3 circles. And that's why you're given 3. So you're going to draw some circles. I just drew some random circles on here. Yours are not going to look like this. So I just drew some random circles. This should have actually been even all the way around in distance. You're going to draw perfect circles, not ovals like mine are, like this around each one. You can use a compass to do this, or you can also use scrap paper to do this. And by compass, I mean like one of these things where you put your pencil in here and you've got this thing. And what you would do is you would go to your map scale. You'll go to your map scale and you will adjust your compass to be the distance that you're looking at, right? Or you can take a scrap piece of paper and you can mark the distance and then just do a whole bunch of little dots around the thing, measuring out. I need yet another scrap piece of paper. Where did my notepad go? I have an adorable notepad here. It says one step at a time. So what I would do is I would take my scrap piece of paper and I would find the desired distance, because I know that this location and this location are X distance from the epicenter. So say I'm going with 3 here, where I wrote my crappy little 3, and I'm going to mark. These aren't even. It's so bad. I'm going to mark. Wow, these 2 pieces of paper are getting stuck off on each other. Sorry, guys. The distance of 3 on there. And then I'm going to take my scrap paper and I'm going to put one corner on the location of the seismograph. And I now have a representation of the distance, how far away the earthquake was. And I'm going to draw a circle around it, that distance away from it. So you can just use a piece of paper and make a bunch of dots and then draw in your circle. Hopefully that makes sense. If it doesn't, you can email me and we'll do like a live chat about and answer those questions for you. And then where those 3 circles intersect is where your epicenter is going to be. If your circles look like this, I cannot draw a perfect circle, guys. Let's get some colors in here. Sorry, last minute demos. If your 3 circles look like this and have 4 spaces in that triangle shape, you did it wrong. And you need to go back and you have to do your wedge diagram measurements again. This is wrong. What you want is for your 3 circles to all intersect at one spot. See, here I only have 2 circles that are intersecting. I only have 2 circles intersecting at each point where those lines cross each other. There's only 2 circles crossing each other. You need all 3 circles to overlap at one point. Let me draw kind of another slightly more realistic what you're probably actually going to be looking at. Grab a green pencil here. Oh, I don't have a green pencil, but I have a green marker here. This is probably more realistic to what you guys are going to have, is where you'll have 3 circles of different sizes, small, medium, and large, and all 3 circles are going to intersect at one point. If you get a triangle in the middle, You did it wrong. You have to go back. I will mark you down points. So you can freeze this later if you're doing your lab and you're like, what did she say? You want it to intersect at one spot. Right there. And you really do want them to be right on top of each other. If you have like this teeniest, tiniest triangle, like it's super itty bitty, that's okay. But it needs to be extraordinarily tiny. Do your best to get them to intersect at one spot. Try and be as accurate as you can with your how you measure the time distance between the P and S wave arrivals. That if you're off in your estimate between how much time there was between the arrivals of those two waves, that's what's going to cause your circles to be off, and you have to start over from square one. Thankfully, you only have 3 seismographs. Anyways, we're almost out of time here, so let's see if we can chat about earthquakes associated with plate boundaries. So, slide 28. The Circum-Pacific Belt convergent boundaries experience 95% of earthquakes. 95% of earthquakes occur. By Circum-Pacific Belt, I mean Ring of Fire. So 95% of earthquakes occur along the Ring of Fire. Megathrust faults, as we said before, generate the largest earthquakes. Welcome to Home Sweet Home. We haven't had one in a long time, which is why you should learn about slow slip earthquakes. Because we haven't had one in a long time is why you should learn about slow slip earthquakes. Anyways, earthquakes along the Alpine Himalayan belt, which is that yellow zone on the map below, are caused because of continental collision. So that is also a convergent zone, just like the Ring of Fire has a convergent zone all around it, because like all the plates are encroaching on the Pacific plate, because they're all like, hey, we're all going to gang up on you. Anyways, don't gang up on people. And then the Alpine Himalayan belt is a crustal, continental crust that's converging. And that causes some earthquakes there, but it is not most of the earthquakes. Again, 95% of earthquakes are along the Ring of Fire. Let's go ahead and look at slide 29. Weak earthquakes occur along oceanic ridge systems because there is some tension pulling those plates apart from each other. So a lot of oceanic ridges, right, are being pulled apart. You also do have some on land rifting. And I assume that you can also have some earthquakes there because you're having tension pulling those apart. Cyclical earthquakes, as we mentioned before, occur along transform strike slip faults. So a transform fault means that it's actually on the plate boundary and is transform. Strike slip does not need to be on a plate boundary. So strike slip can still happen either on those plate boundaries or it can happen away from plate boundaries. You can also have normal and reverse faults, not exactly on the plate boundary, but usually they're near one. All right, so, but most faults are near Earth, are near plate boundaries. That's just the nature of the game because that's where the stress is building up or the tension is occurring. Let's look at our last slide, guys. Slide 30. Slide 30. Now let's talk about earthquakes that are not at plate boundaries. So remember, Earth's crust is broken up into these different plates. We talked about earthquakes that occur at plate boundaries where either the plate is moving away from another plate. I'll do it like this, where one plate is moving away from another plate, or perhaps the plates are converging, or the plates are moving side to side. But let's talk about plates that, or earthquakes that don't occur on the edge of a tectonic plate. Let's talk about the ones that occur in the middle. So these are called intraplate earthquakes. And by intraplate, I would spell it like this in case you're like me and can't spell. This is how it is spelled. Intraplate earthquakes. Intraplate earthquakes are less frequent. They don't occur very often. They're pretty rare. And how are these earthquakes generated, you might ask? Because we don't have tectonic processes going on. We don't have pulling apart like at a major tectonic boundary. We don't have collision at a tectonic boundary. And we don't have side-to-side motion at a tectonic boundary. What is causing the earthquake? These are generated from areas of ancient crustal weakness. So what you're looking at in the diagram below is kind of an area where some areas where there are, oh, excuse me, I apologize. You're looking at an area where there is some maybe failed rift zones. And as a result, you do have some faults and the ground is kind of weak there. And basically like settling of contents occurs. You know, some settling of weak contents occurs, and you get an intraplate earthquake. So, ancient crustal weakness. I can't say that it's always like settling of earthquake, but in any case, it's generated in areas where the crust is weak from a long ago ancient event that took place and weakened the crust and made it not very strong. These produce large areas of structural damage. So the earthquake shaking in an intraplate earthquake is really bad because the earth there is very brittle. And that brittle stuff, it doesn't like move as nice and fluidly. It's like, you know, so the earthquakes there can be quite devastating in an intraplate earthquake. And there have been devastating ones in the past that have caused a lot of damage. These earthquakes can also be felt from a larger distance away. So typically here, I think that earthquake waves around like, you know, plate boundary earthquakes usually only travel like, what was it, like 30 miles or something like that. And then the shaking thereafter significantly decreases. However, with intraplate earthquakes, because the crust is so brittle, they travel significantly farther. Like intense shaking travels significantly farther. So the underlying bedrock in these places is older and thus more rigid. Is what you can fill in the blanks there on that last bullet point. And that concludes our lecture at 4:50. Woohoo! Ending right at a good time. So when we get back together on Thursday, we will talk about kind of intensity and magnitude. We won't go too in depth with those because we won't have time. And we will talk about earthquake damage. We'll talk about earthquake safety. And we will also talk about liquefaction. And we will talk about tsunamis. A lot on the plate. The East Campus Biweekly Digest, but I couldn't access the document without requesting access. Was that important? I didn't realize that you guys didn't have access to it because they told me like to share the document with you guys. So I thought I could share the document. I will repost the document in the comments on that. Or actually, I'll include it in my new announcement because I have to make a new announcement about the extra credit. The East County Campus Biweekly Digest is basically the happenings that are going on at the East County campus. So it includes stuff like, oh gosh, I lost it. Hold on. I closed that tab. I have to find it again. Go to announcements. You guys should probably get it in your email too. But it includes topics such as some student services, East County holding the first virtual information session for students interested in enrolling in an English or GED classes. Also, some information about how Comcast is providing free internet access for 60 days to low-income families. And there's also free internet at Xfinity hotspots. And I guess they've also suspended their data plan rules or something like that. I don't know. And then there's a link for more information about all of these things. And letting you guys know that the summer schedule is out. And also, are you an EBCC East County who would like to share their EBCC story? And then they're like, share your story with us. I'll post it though. But anyways, it's basically just all the happenings and all the things that services that East County is providing and etc. So as a student, it can be helpful to know like events that are going on because these are resources to help you out with, choosing like classes or perhaps extra resources just to help you as a student trying to get internet or advice with other things. Or sometimes they have scholarship information in there too. I always try to pass on that kind of information like scholarships. But yeah, so if you guys have questions and would like to do a live chat, I see that Noah wants to do a live chat. If anyone else would also like to join the live chat, please let me know in the comments. And again, the midterm is on Wednesday. Please be there at 3 online and to take the exam. And otherwise, good luck studying. Make notes for the exam that you can have. I do not recommend using Google for the exam. The information on Google is not necessarily the same or all of the information that's in your book and that I am teaching you guys. Sometimes it's general and not detailed enough. So you definitely, or it's just wrong too sometimes. So you'll definitely want to use your own notes in the book. But yeah. So otherwise, I'll see you guys Thursday. I will leave this up for just another minute to see if anyone else comments and wants to join for the live chat. All right, well, I don't see anybody else in the comments wanting to join for live lecture or for live Q&A. So I will end the live stream and I will see you guys on Thursday for lecture, Wednesday for the exam. All right. Cheers.